Welcome to the Explainer, everyone. Okay, today we are stepping right into the high-stakes, literally high-temperature world of industrial power modules. If you're working in power electronics, you already know the drill, right? The demand for higher efficiency and greater power density, it's just relentless. We are constantly, and I mean constantly, pushing the boundaries of what our systems can actually handle. But as we ramp up that power density, we inevitably slam right into a massive roadblock: heat. It is the ultimate enemy of reliability. So today, we're going to look at exactly how SiC Semiconductor is tackling this challenge head-on with their SiC MOSFET industrial modules. Think about a glowing silicon carbide wafer. It perfectly captures the extreme environments our modern electronics have to survive in. And it really begs a critical question for any design engineer. What actually happens when traditional power modules hit their absolute thermal and physical limits? I mean, when silicon IGBTs start choking on switching losses and standard ceramic substrates literally start cracking under the thermal stress, how do we keep the grid running or the solar fields pumping? What about keeping energy storage systems safe? Well, the answer lies in fundamentally rethinking the whole shebang, both the semiconductor material itself and the physical packaging around it. Okay, let's dive into this. Here's our roadmap for today. First up, elevating power electronics reliability. Second, the Si3N4 substrate advantage. Third, exploring the module lineup. And finally, we'll wrap up with some real-world efficiency data. All right, Section 1, elevating power electronics reliability. You know, every single day, electrical engineers are fighting this two-front war against immense thermal shocks and those pesky parasitic switching losses. And to win this daily battle, SiC Semiconductor approaches these industry-wide headaches by basically taking a page straight out of the electric vehicle playbook. They're applying automotive-grade design philosophies directly to these industrial modules. So, what does that actually mean for us? It means engineering for an exceptionally high standard of ruggedness right from day one. They're combining really comprehensive power electronics and thermal simulation support with silicon carbide's inherently low on-resistance and super minimal switching losses. And the result? You get a module that doesn't just survive in these harsh industrial environments, it actually thrives, giving us dramatically higher reliability and power density compared to traditional silicon setups. Moving right along to Section 2, the Si3N4 substrate advantage. Okay, zooming into the microscopic level, the data on materials is honestly incredibly revealing. While the silicon carbide chips usually get all the glory for their lightning-fast switching, there's actually an unsung hero inside these modules keeping the whole thing together under immense stress. Traditional power modules usually rely on aluminum oxide or aluminum nitride laminates. But the problem? When you subject them to severe temperature cycling, heating up and cooling down super rapidly, the mismatch in thermal expansion coefficients causes these legacy materials to fail. Specifically, they delaminate. The copper foil literally peels away from the ceramic after about 1,000 temperature shocks. And yeah, that means instant module failure. But SiC Semiconductor uses a silicon nitride, or S3N4, ceramic substrate. Under those exact same brutal testing conditions, the S3N4 maintains excellent bonding strength without any delamination at all. I actually just want to pause on this number right here, 1,000. Surviving 1,000 violent temperature shocks without degrading? That is a massive testament to the exceptional power cycling capability of this silicon nitride substrate. Think about it in the real world. Whether your system is sitting out in a freezing solar farm overnight and then baking in the midday sun, or it's rapidly ramping up heavy industrial loads, this specific material choice translates directly to years of added operational life. It is quite literally the physical foundation of reliability. Let's move to Section 3 and see how this builds, exploring the module lineup. Let's see how this robust core technology actually gets packaged for different use cases. SiC offers two highly versatile packages right out of the gate: the 34mm module and the P-Core 2 E2B. What's really fantastic here is the integration of press-fit contact technology. If you've ever had to deal with traditional soldering for heavy power modules on complex PCBs, you know for sure it can be a massive manufacturing bottleneck. These press-fit pins provide a highly reliable, completely solderless mechanical and electrical connection. It totally streamlines your manufacturing process while maintaining that high automotive-grade reliability we were just talking about. Next up, let's spotlight the EED3 module, specifically the BMF540R12MZA3. This thing is a 1200-volt half-bridge beast. It's designed with a heavy-duty copper base plate to highly optimize heat spreading. But the real standout feature, the real game changer for circuit designers, is its ultra-low stray inductance. We're talking coming in at under 14 nanohenries. When you're switching at the blazing fast speeds that silicon carbide allows, high stray induction is your worst enemy. It'll cause catastrophic voltage spikes and ringing. By engineering that straight inductance down to under 14 nanohenries, SiC allows you to safely utilize the full switching speed of those SiC MOSFETs without totally destroying your circuit. And the electrical schematic for that half-bridge topology brilliantly illustrates exactly what's going on inside the package. Notice what's tucked right off to the side of the circuit. It's an integrated NTC temperature sensor directly inside the module. So you don't have to guess the junction temperature anymore, or mount some external sensor to the heatsink and try to calculate the thermal lag. Nope. You get real-time, highly accurate thermal monitoring straight from the source. It is an absolutely crucial feature for designing safe, responsive over-temperature protection in your high-power converters. All right, finally, Section 4, Real-World Efficiency Data. Now, what's really interesting is this direct head-to-head comparison in a demanding buck topology, stepping down 800 volts to 300 volts at a massive 350 amps of output current. We're looking at the basic ED3 module pitted right against top-tier legacy IGBTs from Fuji and Infineon. If you check out the carrier frequencies, the legacy silicon IGBTs are locked in at a 2.5 kHz switching frequency, but the basic SiC MOSFET module is tested at 2.5, 10, and even 20 kHz. What does that actually mean for you? It means you can shrink your bulky passive components, like your inductors and capacitors, significantly. And that leads to a much smaller, lighter, and way more efficient overall system design. So the crucial point here is how the module actually handles the heat generated at these crazy high speeds. The data shows a thermal resistance from junction to heatsink of just 0.086 Kelvin per watt for the basic module. Honestly, this is a phenomenal metric. It translates to significantly cooler operation at high power levels. Because the module is just so efficient at transferring heat away from the chips, right through that silicon nitride substrate and the copper base plate, you can safely get away with using much smaller heat sinks, and that drastically improves your system's overall power density. When you combine all of this, that super low thermal resistance, the ability to switch at 20 kHz without burning up, and the incredible mechanical ruggedness of the Si3N4 substrate, you unlock just massive potential across the most demanding industries. I mean, these modules are tailor-made for high-capacity energy storage systems, next-generation solid-state transformers, and those massive photovoltaic inverters. They provide the extreme reliability you need for railway traction, the high frequency required for induction heating, and that rock-solid dependability that is just absolutely essential for uninterruptible power supplies. Which brings us to our final thought for this explainer. The landscape of power electronics is shifting so rapidly toward these high-efficiency, high-frequency silicon carbide architectures. With power density requirements reaching entirely new heights, you really have to ask yourself, is your current traditional power module holding your design back? Are you sacrificing efficiency or risking long-term reliability with legacy substrates? The data we've looked at today strongly suggests it might be time to rethink what's at the core of your power systems. Thanks so much for joining me on this explainer, and keep pushing the boundaries of what's possible.